Thanks for joining me in today's lesson. In this first tutorial, we will construct Pascal's triangle and we will expand binomials using Pascal's triangle. We are in our final section in chapter 11, 11.5, and we're looking at binomial expansion. Here's Pascal's triangle, or at least the first 6 rows of Pascal's triangle. What I'd like you to do is pause the video and see if you can figure out the pattern in Pascal's triangle in each row of numbers. We've got the first row is 1, and then 1, 1, and then 1, 2, 1, and so on and so forth. Pause the video, see if you can figure out the pattern, what's happening, where are these numbers coming from, and can you create the next row, and possibly the next row. Pause now and see if you can find the pattern. So hopefully you saw a pattern. The first thing you might have realized is that this is a triangle and it is exactly symmetrical. For example, this fifth row goes 1, 4, 6, and then back down for 1. You also might have noticed that all of the rows begin and end with a 1. So I know that the next row is going to begin with a 1. I know that the next row is going to end with a 1. The question is, where is this 10 coming from? Where is this 3 coming from? Where did this 5 come from? And here's what Pascal's triangle does. Each number is the sum of the two numbers directly above it. For example, this 1 and 1 add up to become 2. And then the 1 and the 2 add up to 3. 3 plus 3 is 6. 4 plus 6 is 10. So every two numbers, consecutive numbers, add up to be the number in the next row in between those two numbers. So obviously this next row begins with a 1 because all the rows will begin with a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is back down to 15, and then 6, and then 1. And this pattern will continue forever, ultimately. You can go as far as you want to try to go. This is Blaise Pascal's triangle. What a fantastic name. Blaise Pascal's triangle. And what this triangle represents is coefficients. This triangle is a bunch of coefficients of binomial expansion. For example, the first row, I'm going to try to do it over here, will equal the coefficient for expanding the binomial x plus y to the 0th power. Now obviously anything to the 0th power is just 1. That's why the first row is just a 1. The next row, I'll try to do it over here, would be x plus y to the first power. If we expand x plus y to the first power, well, obviously that would just be 1x plus 1y. The coefficients would be 1x and 1y. The next row is the expansion, at least the coefficients, for x plus y quantity squared. If you multiplied x plus y times another x plus y, you would get x squared plus 2x plus y squared, or rather the coefficients 1 x squared, 2 xy, 1 y squared. So this is pretty cool, and this pattern continues. If we wanted to cube a binomial, we do not need to FOIL 2 times or 3 times. We could look to Blaise Pascal's triangle and see that there are going to be 1, 2, 3, 4 terms, and that the coefficients would go in that order, 1, 3, 3, 1. We would of course have to figure out our variables, and that's not too difficult according to the pattern as well. The next one would be x plus y to the 4th power. The next row has all of the coefficients for x plus y to the 5th power, and so on and so forth. The row that we just created would be the coefficients for x plus y to the 6th power. Now, because of this 0 power, our rows are a little bit off. For example, if I want to raise a binomial to the 4th power, I'm going to use the row that has the 4 in it. Now notice that this is not actually the 4th row because of this 0 row. This is the 0 row, then the 1 row, then the 2 row, then the 3 row, then I call this the 4 row. It's technically the fifth row, but that's just because we started with the 0 exponent. So our pattern is a little bit off because of that 0. So just understand whatever the exponent you're raising your binomial to, understand that the row that you'll be using of coefficients is the row that has the second term as that number. And I would call this the 6th row. So let's put Pascal's triangle to action, and let's look at this binomial expansion, x plus y to the fifth power. Now what that means is there are 5 binomials, all x plus y, all multiplied together. If we wanted to try to do that by the FOIL method, that would take some time. But instead, what we can do to expand this binomial, we can use the 5 row of Pascal's triangle. Now that's the row that has the 5 in it. So the first thing I'm going to do is I'm going to write down the coefficients of the 5 row. Now I'm going to spread them out because there are a bunch of things that go in between them. So that 5 row is 1, and then a 5, and then a 10, and then another 10, and then another 5, and ending with a 1. I'm spreading these all out because each one of these is going to represent a specific term. And you understand if you're raising to the fifth power, there will be 6 terms. 1, 2, 3, 4, 5, 6. The next thing we need to do is, well, I like to go in this order, is I'm going to take the first variable that I have and basically put them on each of the terms. I'm going to put it in parentheses. Right now it's just an x, I understand, but maybe it's a 2x sometime, or a 3x, or even a negative 5x. And these exponents are going to start to decrease from the fifth power, which of course is where we will be starting, down to the fourth power in the next term, down to the third power in the third term, down to the second power in the fourth term, down to the first power, and then all the way down to the 0 power. So you can see I'm basically just counting down from the exponent that I'm starting with, 5, 4, 3, 2, 1, and the 0. Some people don't include this because, of course, anything to the 0 power is just the 1. So that's the first variable. The second variable, in this case, is a y. I'm going to do the same thing, but I'm going to count upward from the 0 power to the first power to the second power, and then cubed, and then to the fourth, and then to the fifth. Oops. Put it in parentheses and raise it to the fifth power. Or what some people might do is they might start on the other side and count down, 5 to 4 to 3 to 2 to 1 to 0. And now I'm going to separate each one of these terms, of course, with a plus sign. These are 6 separate terms. And now all I have to do is get rid of the parentheses and just basically do all of the multiplication. First thing I want to look at is each one of these terms. If you notice the exponents all add up to 5. And that will always be true with this pattern as well. If we're raising to the fifth power, at least in our initial setup, your exponents will always be the numbers that add up to 5. 5 and 0, 4 and 1, 3 and 2, and then their reverses. So let's figure out what this term is. 1 times x to the fifth times y to the 0. You must do your exponents first. We'll do x to the fifth and y to the 0. And basically this term just turns into x to the fifth. Then a plus sign. My exponents must come first, so I have to do x to the fourth, which of course is x to the fourth, y to the first, which is just y, and then multiplied by 5. So I get 5 x to the fourth y. Next, I have x cubed, y squared, multiplied by 10 is 10x cubed, y squared. Next, x squared, then y cubed times 10, and there's our 10x squared, y cubed. Next, x to the first, y to the fourth times 5. So this is pretty simple now. And then our last term, x to the 0 turns into a 1. 1 times y to the fifth, of course, is just y to the fifth. And this is the expansion of x plus y to the fifth power using Pascal's triangle. And in fact, in our answer, you can still see the row of Pascal's coefficients, 1, 5, 10, 10, 5, 1. I'm going to show you another method that we can use to expand a binomial, but I'll do that in the next tutorial. I'd like to flip over to example 2. So here is example 2. I would like to expand 2x minus 3 quantity to the 4th power. And I'm going to use Pascal's triangle again. I'm using the 4 row. Again, that's not the 4th row. It's the row that has the 4 in it. So I've got 1, and then 4, and then 6, and then 4, and then 1. So these are my 5 coefficients. Now I'm going to use my first variable, which in this case is a 2x, and start my pattern with 2x to the 4th power, 2x cubed, 2x squared, 2x to the first. I'll put the little 1, and I'm not even going to bother with this one because I don't want to confuse anybody. It's basically anything to the 0 power will be 1 still. My second variable is not actually even a variable. It's a -3, and keep the sign with it because we're going to see what happens with this one. But it's still going to be the same thing. I'm going to, actually, maybe I'll just start over here. -3 to the 4th, -3 to the 3rd, -3 squared, -3 to the 1st power, and again, -3 to the 0 power is just a 1, so I'm not even going to put anything there so as not to confuse. I'm going to separate my terms temporarily with plus signs, but you see what's happening. We do have a negative, and every time the negative is to an odd power, it is going to change the sign of that term. This is my initial setup. You can see the 5 coefficients of Pascal's triangle, and then of course you see your pattern, and I tried to color code that for you. Now let's simplify each term. The exponent comes first, so I have to do 2 to the 4th power and x to the 4th power. So 2 to the 4th power is 16, and x to the 4th power, of course, is x to the 4th power. My next term has 2 cubed, x cubed, and -3 to the 1st. Because it's an odd power with that negative, I know that I'm going to have a negative term. 2 cubed is 8. -3, of course, is just -3. 4 times 8 times -3 is 96, or -96 x cubed. I know my next term will stay positive because I must now have a negative raised to an even power, which keeps it positive. 2 squared, x squared, and -3 squared, all times 6 is 216, and then the x squared. My next term then must alternate to a negative, and you can see that we have alternating terms. 2 to the 1st, of course, is 2. -3 cubed is -27. 4 times 2 times -27 actually is also 216, but this time with a negative. And then lastly is going to be positive. -3 to the 4th power is 81. This is our final answer. You can see that there still is a pattern, at least in the exponents, 4, 3, 2, 1, and then 0, but Pascal's triangle, at least the coefficients, are sort of hiding now. You don't see the 1, 4, 6, 4, 1 anymore, and it's because one of the variables, actually both variables, or both parts, had numbers in them. So the numbers have all changed, and there you go. A whole lot easier than multiplying that binomial times itself 4 times. So that's Pascal's triangle, and in the next tutorial, I'll show you an alternative way to do our expansion. Thanks for watching this one.